In this unit, ultimately our goal is going to be to understand how some really common chemical reactions happen. These reactions are called hydrolysis and condensation. And as we're going to see as we progress through this course material, these two types of chemical reactions form the absolute foundation of building up biomolecules like proteins, DNA, and fatty acids. Okay, but before we do that, let's first think about the challenges, the energetic challenges that go into a chemical reaction. So we're going to think about this in the context of a very simple chemical reaction. We're going to think about the conversion of hydrogen and chlorine gas to two equivalents of hydrogen chloride. All right, but let's think really critically about what has to happen for this chemical reaction to occur. All right, so we have a hydrogen molecule and a chloride molecule that are all floating around in space. Right? And as they're floating around in space, at some point they're going to bump into each other. And this collision is what induces the chemical reaction. Right? And this process we're going to talk about a lot more when we discuss kinetics. But for now, let's just make an assumption. And that assumption is that for this chemical reaction to happen, we first need this hydrogen to split apart into individual hydrogen atoms. We need this chlorine molecule to split apart into individual chlorine atoms. Right? So we need to break the covalent bond that's holding these molecules together. And once that happens, now we can have a collision between the hydrogen and the chlorine. So these two lone pairs will interact and form the new bond in hydrogen chloride. So we end up with hydrogen, hydrogen, a new bond between hydrogen and chlorine, and chlorine. Right? So we have two major steps here. The first step is breaking all of the bonds in our reactants, right? So we are breaking apart this HH bond and we are breaking apart the Cl-Cl bond. Whenever you break bonds, it takes energy. And the second step, right, so the second step is occurring here where we're creating this new covalent bond between hydrogen and chlorine atoms. And whenever we create bonds, that releases energy. All right, so we really have two big energetic steps here. Okay, so if we think about our reaction progress, and you may or may not have seen diagrams like this before, but the idea is that on the x-axis we have energy, and in this case we're specifically going to be looking at enthalpy, so H here, okay, and we'll label it in kilojoules per mole. And on the y-axis, we are looking at reaction progress. So we are progressing from reactants to products. At the very, very beginning, we have just our reactants. And our reactants are a specific energy. So we have our reactants here. And in our case, our two reactants are a molecule of hydrogen and a molecule of chlorine. So the idea here is that this reaction progresses through a very, very, very high energy state, where in our high energy state, we've ripped apart our hydrogen and our chlorine atoms. So this is our high energy state where we have unpaired electrons, which we know when we have unpaired electrons, it's really stable. Right? So to create this intermediate, this transition state that we must proceed through, it takes a lot of energy. But once we make this intermediate, once we get to this state, we can then proceed back downhill to reach our products, which are at lower energy. So in this case, our products are two equivalents of hydrogen chloride. So we have our HCl here, and we have two of these. Right? So what we very clearly observe here is that to get to our transition state, so this state right here is known as our transition state. it takes a lot of energy. So we go from the energy of our reactants up to the energy of our products. So we have this really, really big uphill climb to get from reactants to products. And as we'll see later on in the class, this is known as our activation energy. This is energy that is required for the chemical reaction to occur. Once we reach our transition state, we now have this nice downhill slope where, all right, so this difference in energy here is energy that we get back, that's released. But the punchline here is that you have to first put in energy for a chemical reaction to proceed. And that's a really important concept to grasp. Chemical reactions require an activation energy. Okay? And if the molecules don't have enough energy to overcome this energetic hump, the chemical reactions cannot occur. So I'm going to go ahead and stop here for this first video. The really big take-home message for this video is that every chemical reaction must proceed through a high energy transition state. To reach this transition state, it takes energy. And that energy that it takes can make a reaction very, very unlikely because the magnitude of that energy can be really large. In the next video, we're actually going to go through an exercise to calculate exactly how much energy it takes for this reaction to reach its transition state, with our ultimate goal being to appreciate the energies it takes for reactions to happen so we can start exploring alternative ways to make some reactions more likely, and if they're more likely, then they're more useful in our bodies.